I'm Alex Warren. I'm working on the ROS to JAUS project.
We created a bridge that opened communication with ROS and its software packages, including a simulator.
One of the real benefits of the ROS to JAUS project is it's going to allow later researchers to spend less time on all the groundwork of getting new sensors to work with the vehicle. JAUS is the Joint Architecture for Unmanned Systems, and it was originally developed by the DoD. Currently, the CAT vehicle runs on JAUS. Both ROS and JAUS allow software to be broken into components, and this allows portability. The old simulator was opaque. It wasn't amenable to extension. It had a very simple command line type output. By using Gazebo for simulation, it allows us to have a 3D visualization of the car. On top of that, it also has access to the Open Dynamics engine, and that is a kinematic physics simulator. So we could get more realistic simulations of the car. Gazebo will allow us to test new sensors. For instance, this Hakuyo laser could easily be added to the Gazebo model, and we could test it in the model without having to go out to a test range. And it will give us information, it will detect obstacles in the simulator. In order to simulate the car in Gazebo, first I need to make a rigid body model of the car using Gazebo's SDF format. Basically an XML format describing the different links and joints that make up the car. The plugin accepted the same commands that we send to the car: gas, brake, and steering. I designed the code so that it would mix these input signals into realistic output behavior. At the same time, I allowed many parameters to be changed at runtime. I allowed steering radius, engine torque, moment of inertia, all of these, along with 40 others, to be changed dynamically at runtime. That's why I implemented a genetic algorithm to search through those possibilities. To get data to validate the simulator, we basically took the car out and I recorded all the commands that it was getting, as well as the speeds of each wheel. This allowed me to feed back in those same commands into my simulator and check whether the wheel speeds in the simulation were running at the same speed as in the real car. The genetic algorithm starts with a population of individuals, each represented by parameters chosen at random. The algorithm evaluates each individual by running the simulator and returning the error that came out. The algorithm takes a population, it evaluates all of them, and then it goes over that population, either mutating or mating a number of the individuals, and it comes up with a new population. And then, with the new population, it evaluates them again, and then it goes through this cycle of generations. Slowly, the population changes. Over time, the population will converge upon good solutions.
I just want to thank everyone with the CAT Vehicle project. I really learned a lot from you guys.